Hi one and all, this is Steven from Aero B section. Today I am taking mathematics tech talk. My topic is a Fourier series experiment. Fourier series. Fourier series in mathematics. A Fourier series is a periodic function composed of harmonically related sinusoids combined by a weighted summation with appropriate weights. One cycle or period of the summation can be made to approximate an arbitrary function in that interval or the entire function if it too is periodic. As such, the summation is a synthesis of another function. The discrete time Fourier transform is an example of Fourier series. The process of deriving weights that describe a given function is a form of Fourier analysis. For functions on unbound, unbounded intervals, the analysis and synthesis analogies are Fourier transform and inverse transform. Since Fourier's time, many different approaches to defining and understanding the concept of Fourier series have been discovered, all of which are consistent with one another. Some of the more powerful and elegant approaches are based on mathematical ideas and tools that were not available at the time Fourier completed his original work. Fourier originally defined the Fourier series for real valved functions of real arguments and using the sine and cosine functions as the basis set for the decomposition. Many other Fourier related transforms have since been defined, extending the initial idea to other applications. This general area of inquiry is now sometimes called harmonic analysis. A Fourier series, however, can be used only for periodic functions or for functions on a bounded compact interval. Function f of x is a sum of six sine functions of different amplitudes and harmonically related frequencies. Their summation is called a Fourier series. A Fourier transform f of x s of f in blue, which depicts amplitude versus frequency, reveals the six frequencies at odd harmonics and their amplitudes 1 by 6. Look the picture, the wave the lines are curved but there is no wave frequency. Let's go into that picture. And next, the definition of a Fourier series experiment. Consider a real valve function s of x that is integrable on an interval of length p, which will be the period of the Fourier series. The correlation function It is a correlation function SF xf of t delta is called integral p s of x into cos of 2 pi f of x minus t into dx. Essentially, a matched filter with template cos of 2 pi fx. Its peak value is a relative measure of the presence of frequency of f in function s. The analysis process determines for certain key frequencies the maximum correlation and the corresponding phase offset Tf. The synthesis process, the actual Fourier series, in terms of parameters to be determined by analysis is, let's see the Fourier series amplitude phase form. Sn of x is called a naught by 2 plus sigma n is called 1 an into cos 2 pi by 2 pi by p n of x minus psi n. This is called equation 1. In general, integer n is theoretically infinite. Even so, the series might not converge or exactly equate to s of x at all values of x, such as a single point discontinuity in the analysis interval. For the well-behaved functions typical of physical processes, equality is customarily assumed. Integer n used as an index is also the number of cycles of the nth harmonic in interval p. Therefore, the length of a cycle in the units of x is p by n. The corresponding harmonic frequency is n by p, so the nth harmonic is cos 2 pi x of n by p. Some texts define p is called 2 by pi to simplify the argument of the sinusoid functions at the expense of generality. Clearly, equation 1 can represent functions that are just a sum of one or more of the harmonic frequencies. The remarkable thing for those not yet familiar with this concept is that it can also represent the intermediate frequencies and or non-sinusoidal functions because of the potentially infinite numbers of terms n. Let's go to the picture. The sum of the sinusoidal components of a Fourier series is a periodic function, whether or not the original function s of x is periodic. Fourier transform a function s of t which is not shown. In this first picture, s of t is not shown. S of f, s of t S of t give rise to S of x, S of f, and the second picture transform of a periodic summation of S of t Fourier series coefficients. And third picture shows transform of periodically sampled S of t discrete sine Fourier transform. And fourth picture shows transform both periodic sampling and periodic summation discrete Fourier transform. If S of t is a function contained in a interval of length p and 0 elsewhere, the upper right quadrant is an example of what its Fourier series coefficients a of n might look like when plotted against their corresponding harmonic frequencies. The upper left quadrant is the corresponding Fourier transform of S of t. The Fourier series summation not shown synthesizes a periodic summation of S of t, whereas the inverse Fourier transform, it is also not shown, synthesizes only S of t rather than computationally intensive cross correlation. Fourier analysis customarily exploits a trigonometric identity an into cos 2 pi by pi nx minus psi n is equal an into cos of psi n, an into cos of sin n is total called as simply an. Convergence. In engineering applications, the Fourier series is generally presumed to converge almost everywhere. The expectations being a discrete discontinuities, since the functions encountered in engineering are better behaved than the functions that mathematicians can provide as counter examples to this presumption. In particular, if S is continuous and the derivative of S of n, which may not exist everywhere, is square integrable, then the Fourier series of S converges absolutely and uniformly to S of x. If a function is square integrable on the interval x of 0, x of 0 plus p, then the Fourier series converges to the function at almost every point. Convergence of Fourier series also depends on the finite number of maxima and minima in a function, which is popularly known as one of the Dirichlet's condition for Fourier series. See convergence of Fourier series. It is possible to define Fourier coefficients for more general functions or distributions. In such cases, convergence in non or weak convergence is usually of interest. Let's go into complex Fourier series. An example of the ability of the complex Fourier series to trace any two-dimensional closed figure is shown in the adjacent animation of the complex Fourier series. Tracing the letter E for only exponential. Note that the animation uses the variable t to parameterize the letter E in a complex plane, which is equivalent to using the parameter x in this article's subsection on complex valued functions. In the animation's backplane, the rotating vectors are aggregated in an order that alternates between a vector rotating in the positive counterclockwise direction and a vector rotating at the same frequency but in the negative clockwise direction, resulting in a single tracing arm with lots of zigzags. This perspective shows how addition of each pair of rotating vectors, one rotating in the positive direction and one rotating in the negative direction, nudges the previous trace shown as a light gray dotted line closer to the shape of the letter E. In the animation's front plane, the rotating vectors are aggregated into two sets. The set of all the positive rotating vectors and the set of all the negative rotating vectors. The non-rotating component is evenly split between the two, resulting in two tracing arms rotating in opposite directions. The animation's small circle denotes the midpoint between the two arms and also the midpoint between the origin and the current tracing point, denoted by positive plus. This perspective shows how the complex Fourier series is an extension, the addition of an arm of the complex geometric series which has just one arm. It also shows how the two arms coordinate with each other. For example, as the tracing point is rotating in the positive direction, the negative direction arm stays parked. Similarly, when the tracing point is rotating in the negative direction, the positive direction arm stays parked. In between the animations, back and front planes are rotating trapezoids whose areas represent the values of the complex Fourier series terms. This perspective shows the amplitude and frequency and phase of the individual terms of the complex Fourier series in relation to the series sum spatially converging to the letter E in the back and front planes. Another application of this Fourier series is to solve the Bessel problem by using Parseval's theorem. The example generalizes and one may compute 2n for any positive integer n. Thank you all for watching this.